Hey folks, we're about to start another episode of Ask Us Anything about electrochemistry. But before we begin, because we have some extra time, there are a few things I'd like to go over first. While we're waiting for the live stream to start, type your question into the chat. The sooner we get your question, the sooner we'll be able to answer it when the live stream starts. We usually try to answer questions in the order that we receive them, but it's definitely possible that we get so many questions that when your question comes up, we're out of time. If you are a Tier 1 or a Tier 2 YouTube member, you do get priority in us answering your question. You also have the opportunity to join us on the stream to either share slides or talk to us in person about your specific electrochemistry research questions. If you are a Tier 1 or Tier 2 member on our YouTube channel, you will find in the community post the link and password to join us on our broadcasting platform. We get a lot of questions about electrochemistry, whether it's through our YouTube comments, webinars, email, phone conversations. We get lots of questions from people about electrochemistry. And sometimes responding to a YouTube comment or trying to describe a cyclic voltammogram over the phone isn't always the easiest way to teach or describe electrochemistry. That's why we created this live stream. In the Ask Us Anything About Electrochemistry live stream, you can ask us any questions you have about electrochemistry, and we can use better tools and take more time to describe some of these electrochemical processes to help you with your research and understanding of electrochemistry. Now, in our time of doing this live stream, we've observed that if you ask a very specific question, we might not be able to answer it. It'll be a little bit too specific for us. On the other side, if you ask a very broad question and you're interested in just a very broad understanding of cyclic voltammetry, we have separate tools, we have other resources to help you. So we do have a YouTube video on cyclic voltammetry, an introduction to the subject. And if you're interested in more of a long-form course on, say, electrochemical impedance spectroscopy, we have a 5-part EIS webinar series for our Tier 2 YouTube members that you can access at any time. Now, if you weren't aware, Pine Research Instrumentation is a company that produces a wide array of high-quality electrochemical research equipment, from potentiostats to electrodes, electrochemical rotators, cells, different types of accessories. Pine Research has been supporting electrochemistry research and teaching for decades. Recently, we have developed new electrochemical simulation software called Aftermath Live. Aftermath Live is an online streaming platform where you can simulate popular electrochemical techniques like cyclic voltammetry. It's a powerful research tool, as you might simulate a cyclic voltammogram to support an electrochemical mechanism for your redox reaction that you're studying. But Aftermath Live and cyclic voltammetry simulation is also a very powerful tool when it comes to just learning electrochemistry. In fact, in previous episodes of the live stream, we have used Aftermath Live and our simulation software to answer some of the questions that you have. If you are watching this on YouTube, you can get a 10% discount on your first month of the basic and research editions of Aftermath Live by using the coupon code PINEYouTube10 when you're at checkout. Aftermath Live is a powerful tool and you can cancel your subscription at any time. Go to aftermathlive.com to check it out. Link is in the description below. Our live streams are normally on Fridays from 1 to 3 p.m. They normally last about 2 hours, sometimes a little bit more, sometimes a little bit less. If you miss the live stream, you'll always be able to watch it on our YouTube channel, and in the description we put timestamps for every question that was asked. This way you can look through the description and find the questions that are most relevant to your research and then watch those at your leisure. Also, we apologize in advance if we mispronounce your name. If on a YouTube channel you can put anything you want as a name. It could be a Pokemon, it could be a string of numbers. But if we call you out and we accidentally mispronounce your name, we apologize in advance. Lastly, please do not spam the chat. We've had numerous instances of people either talking about inappropriate things or constantly filling the chat up with some kind of spam. We will remove you if you do that. Let's keep the chat very clean and just talk about electrochemistry. Sometimes it takes a while before we're able to answer your question. So if you keep typing your question into the chat and spam the chat, then we will remove you from the chat. But if it's been a while and we may have forgotten about your question, one message as a gentle reminder is all that's required. All right, I think that's all of the housekeeping things. Now, let's start the live stream.
And we are live.
Hello, everybody. Welcome to another episode of Ask Us Anything about electrochemistry.
And I'm still too tall. Look at me.
Look
how tall I am. I feel like I'm not reaching the mic. I hope that I can be heard.
No, you can be heard. And
2 seconds before we start, I'm like, my chair is messed up. I'm trying to fix it, and I feel like a giant. And I kind of like it. I'm not gonna lie. But now the cord is stuck, and I'm all of a mess here. Look at this.
It's all good.
This is what you get with live streaming. You know, you get all the warts and weird stuff, and I can't figure out. It's not like I've been doing this forever. You know, I'm still apparently not sure how to handle it.
No, it's all good.
Great.
It is all good.
Welcome, everybody. We're happy to have you here.
Yes. So we have a couple questions already from people who've sent us stuff. Where do we want to begin? There were questions from last week. There's some questions of people right now.
So there was a question from, this one's probably relatively quick, from Haider Ali.
Mm-hmm.
I think he asked this question earlier in the week, if I'm not mistaken.
Yes.
Was okay. I believe, if I'm not at the time, I'm always sort of trying to remember the timing of this, but it was on this event earlier in the week.
Mm-hmm.
And he said, is it possible to connect the 2 probes of a potentiostat to copper plates and sandwich a pellet in between and take the IV measurements? So the answer is yes, if the pellet is able to function as an electrolyte.
Mm-hmm.
Now, it could be a solid electrolyte, but the point is, consider a let me share my screen and draw a thing here. Sorry, get my PowerPoint ready. That one. That's the one.
Mm-hmm.
Okay. An electrochemical system consists of, I guess if you'd say, if you're doing copper plates here. So this is one electrode and this is the second copper plate, right? And you connect this to your potentiostat. It's like the voltage current source, basically, right?
Mm-hmm.
And so I'm not gonna draw clips. I'm just gonna draw very simplified, right? And so the idea is I have a pellet in between here. So I have something sandwich. I'm drawing it. It's probably way too big, like physically here, just on the drawing, but just to show the example of what I mean, this is the pellet that's squished in between, right? Well, think about how an electrochemical experiment fundamentally works, right? We have electrons that are going to go. It can go either direction, but let's just pretend something is losing electrons here. So there's an oxidation occurring on this side, and we have a reduction occurring on this side. And so electrons are going to travel in this direction. Well, you need charge balance. It doesn't work if there isn't charge balance. So what that means is that in this area here, there must be negative charge moving in the other direction or positive charge moving in this direction, just to have it be balanced. If negative charge is moving from left to right, based on the image you're looking at here, positive charge must move from also left to right, or a corresponding negative charge. Now, usually that occurs with electrolyte. We have liquid system, we have, anions and cations, and that's why you have an electrolyte system. You have, whatever, sulfuric acid, you have H plus and SO4 minus 2 minus, like you have ions that move in solution to balance the charge. So the answer to your question is yes, if this pellet consists of movable ions, basically, right? Movable charge. Now, when you say pellet, the comment wasn't really specific to what that pellet is. And to a certain extent, I'm not 100%, I'm not an expert per se in solid state, like solid electrolyte. Like maybe the pellet's really, really thin actually. And it's, it's like it's some sort of a pellet that's soaked in, you know, ions, positive and minus ions, and so they're like distributed in here, and so there is some mobility, then it probably will work. But again, it just requires um, that attribute is part of your pellet. Then in theory, it should work. It's a charge balancing thing. Because if not, the potentiostat, it just won't. It won't be able to work at all. There's no completion of the circuit. Um, there's no
You wouldn't be able to establish a
Yeah, like, I don't even
potential.
think a potential would show up
It
at all.
wouldn't show up.
I'm thinking it'd be an
Yeah.
infinite resistance or something, like,
Yeah.
nothing would happen, like, the potentiostat would give you nonsense reading, it'd be all noise, or I don't know precisely what you would read, but it would not work, is the long and short of
Mhm.
this. So that's kind of the basic answer, I guess, and the reality, again, is that, um, it's all about charge balance, and so that's, like, the point of the electrolyte that exists between
Mhm.
the working and the counter, electrodes in your system, basically, so.
And I guess one other last point to Hadir's question. It sounds like, that we could do this with a multimeter, but you also say like two probes of a potentiostat. Make sure that when you're doing this, working electrode will be connected to one side, but you would short the counter and the reference on the
Yes.
other side, and that way you can use it as a 2.2 probe experiment.
Yeah, I did not really
Yeah, I
make
didn't. I
that
didn't know.
clear, but
I didn't know
that's
if that was what you were trying. If he was trying to ask that as well.
yeah, I
But yes.
hope that was yeah, exactly. Right. The counter and reference need to be shorted. That needs to be made clear.
Yeah.
Exactly.
All right, that's good. All right, so we can.
So I
that
think
one.
that is the next one this whole set of questions about Tafel or something, or was there another one?
Yeah, so there was so these were some YouTube comments that we could get to later. He
Mhm.
was commenting on some videos that we had, but I think uh Dilly Ram is here now, I believe.
Mhm.
So we can look at his question first.
Yeah, let's
if
do
it's-
that.
So Dilly's asking, "Hi, can you explain the electrochemical differential pulse voltammetry, square wave voltammetry, detection of chromium and arsenic in water? I mean, I want to know what different parameters of DPV are suitable for the above ions and buffer solution." Um, so let's see. So I don't know the potentials of like chromium and arsenic, but for differential pulse and for square wave voltammetry, those are both techniques that are designed to help detect very small quantities of ions, so very low concentrations of things. And the general nature of the technique is that you get rid of background double layer charging current is naturally removed. You also remove a fair bit of quote Faradaic current as well. Background Faradaic current also gets subtracted. Yeah.
Just so you can have it
Yeah.
while you're giving the explanation. Here's the waveform for DPV. For
Yeah. So
instance.
this is the waveform for DPV.
Square wave is similar, but this is DPV just for reference. So
Yeah. And so you step the potential, the kind of EDPH. This is what you kind of step the potential with. That's one of the parameters. So there are three parameters, if you will. There is the pulse height. There's the pulse width. That's how wide the pulse is. And then there's the time from pulse to pulse, if you will. And then you sample maybe somewhere in the middle of an individual pulse. That's like the very small circle at the top, but we're just going to call it the top of the pulse, top of the tower. And so um, you can control all those parameters. So, you also can control like the step height. That's the EDPI, which is at the bottom there. So what you're effectively doing is you're collecting current when you step the potential. You also collect it when before the potential steps, right before it, and you subtract those two. And when you subtract those two, ideally the same amount of time has dissipated, but you're only getting kind of the Faradaic current associated with just that process. I guess I'm maybe not necessarily explaining it the best, but I guess I also want to figure out exactly what his question
I
is.
think it
Does
was
he
more
want us
about
to
the
explain the
parameters.
technique?
Well, I think the question was about like what parameters. So just for what it's worth, I'll just
Hmm.
one last little
Yeah.
share. This is square wave. So just for
Yeah.
reference,
Yeah.
you see
Square.
the
Square.
difference
Simple.
between square wave and differential pulse is basically that the time, the width, which is on the x-axis, which is time, um, is the same for the up and the down parts in square wave. For differential
Hmm.
pulse, you have an asymmetrical thing where the up pulse is short, the down pulse is longer.
Hmm.
And what that effectively means is that basically the difference between differential pulse and square wave is that you have a like a longer, more robust, if you will, background correction part in the DPV than in square wave. In square wave, it's equal, if you will.
Hmm.
You can add more, Alex, if you want in a minute. But I guess my main answer is that I cannot tell you what the parameters should be, and it's a very, I don't know, unsatisfying answer, but it's the truth. Is that um, DPV, square wave, normal pulse techniques have sort of lost the electrochemistry great battle of all time against cyclic voltammetry and linear sweep, right? CV and LSV are the winners. Everybody does those, everybody publishes those. The reality, however, is that pulse techniques are in many ways, in my opinion, much more useful. Um, the difficulty, however, with pulse techniques is that there's way more parameters to pick from, and it is not clear what they should be. And so the answer to your question to a very large extent is I don't know, and neither do you, and you're going to have to figure it out. That's a really crappy answer, right? It's like, well, I don't, well, should I bump up 50 millivolts or 10 millivolts? Should I have it go for 1 second or a millisecond? Like some of those answers are based on like kinetics, which is hard to know exactly. But like, for example, if you have a pulse that goes pulse up in this exact time and like pulse up 1,000, 2, pulse down 1, 2, 3, 4, pulse up, wait, pulse down. Okay. That's like several seconds per pulse or something. Right. And you have a very fast reaction. Like every time you pulse it, it's like immediately decaying. It's immediately decaying. You're getting like very like, like even at the short, let's say, pulse, you're getting like all the kinetic stuff over with, and it's very like maybe that's what you want. Maybe you're trying to like totally get all background information and something like that, right? On the other hand, if you have a very like fast reaction, but your pulse is like up, down, very, 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 very fast pulsing, you might be capturing like the um, very pinnacle of the kinetic like response of double layer charging and the kinetic response, like of the forward pulse. Like you pulse up a potential, you induce a Faradaic reaction, the current spikes, and you immediately drop back down to a background current. And so you're getting this tremendous differential current between where I pulsed, where I'm inducing a Faradaic reaction, and then where I drop back down when it's all background. And so the differential current is very large. What that allows you to do is clarify a peak much more easily in a lot of cases than with cyclic voltammetry, where you're just sweeping the peak until the Faradaic reaction happens. You have confounding effects from the background, from double layer, from non-Faradaic processes. When you're able to pulse, you can like immediately pulse at the E0 or near an E0 of a Faradaic reaction, get a jump in the current, and then immediately drop back down to where it's not happening, and then you increment that. And so the reality is that the speed at which you do that, if it's commensurate with the kinetics, you might get one thing. And if it's much slower than the kinetics, you'll get another thing. And if the effective scan rate, which is like how much you're incrementing up divided by how long the whole thing takes, right? Because there's an effective scan rate that you could compare with cyclic voltammetry, but it's not as simple. Cyclic voltammetry is very simple. It's like how many millivolts do I move per second? Because that's just what it's doing. And DPV, how much you're moving, again, just to bring up the or square wave or whatever, but just to bring up the illustration, right? How much you're moving is that orange thing at the beginning, which is the for one whole up and down pulse sequence, I then increment it up. That's how much I'm moving. And then the time it takes is like the green thing, but not exactly, but basically how
Hmm.
long it takes to go from one little rectangle to the next little rectangle. So it's like how much millivolts I'm jumping per time. In other words, it's a complicated quote unquote scan rate. Okay. And so this is why the answer is that you have to just do a lot of trial and error, because you are working at the kinetics of your reaction and also how far and fast you're scanning and jumping. And if you pick your parameters well, you'll end up getting that really nice big differential current between where the reaction's happening and where it's not happening. And it's like sometimes with CV, you have a huge background current and your peak is like barely visible, right? Like you'll get this kind of curve and then the peak is like very visible. But it's like when you do DPV, it's a differential. So all the background basically goes to zero. And then the peak is more obvious. That's
Hmm.
what DPV often gives you, or square wave as well. So yeah, I think that to a large extent, the answer is that there's a lot of trial and error required for those parameters. And that's probably why CV and LSV are like often used in their place, because it's just easier like conceptually to like figure out, oh, I'll just pick some scan rates and pick some limits and I'm good to go. I don't have to pick the pulse stuff too. Because yeah, the reality is that it can be tough to nail down what those parameters should be for an ideal DPV or square wave plot. But as with all things in electrochemistry, that's the last thing I'll say, is that once you've picked some parameters that you think are representative or helpful or useful for what you're seeing, stick with them so that you can compare data sets, right? Because like that's
Hmm.
the biggest mistake you can make, is that you're constantly changing them. Then when you have catalyst 1 with catalyst 2 or situation 1 with situation 2, how in the world can you compare them when your parameters were different, like wildly different, right? Then you sort of lack the comparative ability. So it is important to make sure you select the parameters, do some trial and error, select them, then use those and apply those across all of your experiments sort of equally. And that will allow some, um, I guess, cross experimental comparisons to be made.
Hmm.
So I know that's kind of a lot, and I do apologize. It's a little bit convoluted, to be honest, but DPV, square wave, they can be pretty convoluted types of experiments. So
Hmm. We have a couple questions in the chat that recently came up. Some people are talking about a talk plot. Um, and it looks like a talk plot is, I'm just looking this up, it's a plot used to determine the optical band gap for a semiconductor. Um, and it doesn't, it has to do with like photon energy. But this is something that
this
I
is not something
don't
I have
know anything
familiarity
about.
with. I don't know if this is electrochemical. I guess it
I
has a
don't think.
potential in it, but energy, it's not. Yeah, I don't know that this is electrochemistry based, to be honest.
Yeah, no, I don't think it's an
Which
electrochemistry
which doesn't mean
based.
we can't answer it. I mean, this is a
Yeah.
live stream about electrochemistry. I mean, we do have some obviously, knowledge of other disciplines, let's just say physics or
Hmm.
whatever. But yeah, I'm not familiar. It's the plot of photon energy and the quantity alpha e to the square root of alpha e.
Yeah,
It's the absorption coefficient, and that's energy, I guess. It's like energy or electron volts. Yeah, I mean it's energy because electron volts is energy. It's
yeah.
it's like photon energy against absorption and energy. Yeah, I don't know that I can answer any of that. The
Yeah.
other question about talk plot, what is it? Why is it used?
Yeah.
Well, I mean it's
I don't
used
know
to
anything
apparently calculate
about it.
band energy, but I guess why is two. Yeah, sorry,
Yeah.
Syed. It looks like there's two different Syedas
Yeah.
here.
Looks like there's two different sites asking
Um,
about talk plot, and
yeah, sorry.
yeah, I don't
I
know
don't.
anything about it.
Yeah, not within our area of expertise for sure, and I'm not entirely sure that it's electrochemical in nature.
Yeah.
Yeah, I guess it's a bit beyond our knowledge, to be honest. So sorry.
Yeah.
I don't think we can really answer much more about that.
Yeah. Electric Studio has a question. Electric Studio asks, what electroanalytical techniques are commonly employed in hydrogen evolution reaction, oxygen evolution reaction, or hydrogen production using electrolyzers? Well, I guess cyclic voltammetry is one, or linear sweep voltammetry is one technique. Rotating disk voltammetry is used quite a bit, mostly because it overcomes some of the mass transport limitations. Sometimes people use EIS because they're trying to analyze, learn more about their catalyst depositions. Um, just looking at just electroanalytical techniques. Sometimes you look like a power plot is another thing
Yeah, so
that people look for.
that comes from a polarization curve.
Hmm.
Um, so this is usually with an electrolyzer. If you're doing HER or OER by itself, it's what you said. It's rotating disk electrode stuff or just LSV CV on a catalyst. But if you're doing a polarization curve and a power plot, what you're doing is either linear sweep voltammetry or a series of chronoamperometry experiments. And so it's plotted like a CV, but backwards. So voltage is on the y-axis usually, and then current is on the x-axis. And it's different for an electrolyzer than for a fuel cell. I kind of think about it in terms of fuel cells. Electrolyzers are the opposite, where you apply a voltage to get a product out. But I'll just draw it for a fuel cell, is that basically the curve ends up looking something like this. And you start off at the sort of the OCV here, and you either sweep the voltage basically down here and you get current out of it as you sweep. This is more for a fuel cell again, so but it's analogous to an electrolyzer, or you just hold the voltage and you do chronoamperometry at a bunch of just different voltages, because the reality is you are trying to eliminate diffusional processes here. So you don't want to, if you do a sweep, you want to do it very slowly to try to get mostly kinetic information. And so you're just basically doing a chronoamperometry, and you're letting the current decay, and you're getting a sort of a steady state value of current all the way down. And then you can do a power curve, which is where you would plot V times I, which is equal to power. And usually it looks like this, something like that. And so you'll have a maximum of power versus current. And so those are the kinds of plots and analyses that people often do with electrolyzers and fuel cells. So at every point, you can multiply the I times the V, and you get some power in watts or whatever. And then you can plot that versus the same x-axis I, and that's a power curve. So power anyway, in watts basically. So those are mostly the kinds of like electroanalytical techniques and plots that are done for fuel cells and electrolyzers quite often.
Mm-hmm. All right. Looks like we got a question from Habg. Habg is asking, can you describe OCV in simplest terms? So he's referring to the open circuit voltage. And the open circuit voltage, usually when we use the phrase open circuit, it means that the circuit is not connected. It has an open lead. So if we just draw a quick picture of that, I was thinking about drawing some stuff for DPV, but in an open circuit system, let's say you have a cell, you have some solution, and then you have you have two electrodes. And this can also be for a battery. A lot of people will use open circuit voltage for batteries, but it really is just for a two electrode system. So let's just say we have two electrodes. This could also be the terminals of a battery. And then we would usually measure, we have a voltage here. And the open circuit voltage is we would describe it verbally as the potential at open circuit, which is to say the instance when this is like this, where it's open, which is to say that no current can flow through the system. So there is no electrons that are flowing between these two working electrodes. So it's the voltage in a two electrode system when no current is allowed to pass. Some people might describe this as a system at equilibrium. Maybe not. In reality, you can't actually measure the open circuit voltage if there is an open circuit like this. So what commonly happens is this is connected, but the resistance in here is super high. So there's what's known as a high impedance uh, object, amplifier, if you will, here that is very, very large. We're talking like maybe tera ohms or so. And because you need to have some current to make a measurement. So because this is so high, the electrons that go through this resistor is very, very low. It actually will not mess up this this measurement of the potential difference between these two guys. So that is the simple answer. That I would say that is the simplest answer of what the open circuit voltage is. It is the potential or voltage, really the voltage between two electrodes when no current is allowed to flow through it. Now, personally, I have always found that answer to not be very helpful in terms of gaining like a kind of a chemical understanding of what the open circuit voltage is. And if you wanted, let me know if you want me to give you a more detailed explanation, because I don't want to waste your time. If this explanation of what the open circuit voltage is makes you happy, that's fine. If you want me to go into more detail, because there is more detail to help you get a better picture of what the the science behind what you're actually measuring, I can tell you more about that. But again, I don't really want to waste your time. But that's the simplest. You wanted the simplest explanation, so that's the simplest explanation. Quite simple. All right, we have a couple new questions coming in. We should go with you want to go in order, or
yeah, I guess. Let me see here.
Or Dooley's is a member. We could talk to Dooley's because we also know him.
That's right. Yeah, he's back again. So recently saw the 5-part EIS webinar. Appreciate it.
Great.
I'm wondering if you increase. Let's see. If you increase the number of data points obtained per decade to 20, can you use Kramer's-Kronig to extrapolate data? The number of points you use per decade is not going to improve your ability to extrapolate. Basically not. So can you use Kramer's-Kronig to extrapolate? Do you mean interpolate? Because like extrapolate means to go outside of the limits. Like the RCT value using data that you may want to remove due to drift from using a pseudonym electrode, a fake name electrode. Like the RCT value using data that you may want to remove due to drift. I don't think I understand what you're asking, because extrapolate means to reach, so to speak, outside of the boundaries, which in this case would be like frequency. And so by taking more points in the middle, I'm not sure how that would allow you to reach, like, I'm not sure that would matter.
I think, and Dooley's, let me know if this is right. I think what you're trying to ask is, because Kramer's-Kronig looks like a circuit fit.
Yeah, it isn't though.
Right. It is not a circuit fit, but it looks like a circuit fit.
We're lying to you. It's not a circuit fit.
It's not a circuit fit. It looks like one, but it sounds like you have some drift in, like, say, the low frequency area, and it's messing up with your circuit fitting. But you were thinking about, if I just increase the number of data points I do in my EIS and maybe exclude the, maybe you want to just exclude some of the low frequency stuff if it's making the Kramer's-Kronig, giving you a wrong answer, because you're ultimately trying to get an RCT value. That's what you want. Because I feel like, because your next comment is like RCT, you might
so
remove
like the drift is okay. Let me put it this way: if you have, for instance, try to again, I think I'm trying to like partly understand what I think the word extrapolate's throwing me for a loop. I think that's the problem. But let's maybe you can comment, check if he ends up coming. But like if you have something where it's like you have a semicircle, right? And then at the end it's like it's noisy or something, or whatever. I'm just making up this stuff. And you do Kramer's-Kronig, and it's probably like tracking pretty nicely, but then it kind of doesn't, right? Okay, so there's noise here, and it's like, well, what you're after is RCT, right?
Yeah.
And it's like, well, all this noise over here is sad, right? Sad face. So adding more points per decade, like, again, the word extrapolate isn't really the right word, I think, but like if you're talking about like add more points per decade, then it's like what it might help you do, I guess, is clarify the point at which it starts going haywire, let's just say. Because if it's like, okay, then it's like, okay, well, when I was here, it's like it was this point or this point, but what frequency exactly? It's like I only have 1, 2, 3, 4, 5 good points, and then I have a bunch of crappy points. Here I have 1, 2, 3, 4, 5, 6, 7, 8, 10 good points. This is all made up numbers, right? Of course. But like on here is where it starts getting bad. So there is something to that where, okay, and Kramer's-Kronig isn't going to help you get a value for RCT, by the way. But like what it would allow you to do is be like, all right, well, okay, so like there. So like what I could do is exclude the points from here on, just get rid of those points. And then when I do my circuit fit, I can get like a value for the RCT. And I have more points with which to include in the fitting algorithm. That could help you for sure. It could help you clarify the frequency at which it's bad, so to speak. Because it's like you do like 5 points per decade and you get like 22 hertz. Okay, well, was it 22 or was it 70? Well, you didn't take any points in between there. So now you take more points per decade. You can like more accurately pinpoint the place that it's bad or something. That can be a thing. But again, I'm just to harp on your first question, maybe that isn't exactly, but when you say extrapolate, that would imply like getting information out here or like be like beyond the limits, like at lower frequencies or at higher frequencies, like that isn't something I recommend in general. And I don't know that more points per decade is going to assist with that kind of a thing, because like, for example, if you, whether it's related to this specific problem or not, with drift or not, the point I'm going to make here is that if you have like a really a data like this, and you want to fit it with an RC, like a void element, because you suspect that this is like a really big semicircle, right? And you're trying to measure this RCT. Okay, like that's reasonable, right? The limitation is here. It's the endpoint. It's whatever your lowest frequency is. And so if you have points in here, and then you like take a lot more points in here, that doesn't matter. Like it doesn't help you. You need to take like lower frequencies in theory, that like you would take more low, like go another decade lower. So it's like, oh, now I can see this clarifying. I'm almost finishing the semicircle. That'll make my RCT measurement, more accurate. But taking more points in between isn't going to do anything for that extrapolation, like the measurement of it. Maybe it makes the fit slightly more accurate, maybe, but also it just might introduce more drift and noise because the whole experiment will take longer. And it's not guaranteed that more points per decade is necessarily going to do a lot for you. So again, this is all like somewhat answering your question, I think, based on my interpretation of it. So yeah, more mid hertz might help. Yeah, but possibly in the way that I described.
Yeah.
But that extrapolation, if that's really what you're after in a sense, I don't know that that's really going to make a ton of difference for you, like in the range outside of where you're already at, because it's whatever the lowest frequency you're at dictates how much you can see, basically. So I hope that's somewhat clear, Julius. You can comment if you need clarification.
Yeah.
There's another Tafel question.
Yeah. Yeah. So
It's like a weekly occurrence now.
I know. Just rename the Manoj has a question.
It's the Tafel
Can
live
you
stream.
we should just rename this Ask Us Anything About Tafel. And then
Ask us anything about Tafel slopes.
Yeah.
That's so funny.
We could have like the Tafel hour. Talk about the Tafel hour.
It's the Pine Research Tafel hour. We got to get it sponsored. Brought to you by whatever.
Tafel. Can you explain about the Tafel slope for HER and how to do the Tafel slope measurement in potentiostat? Let's see. You always have the slides.
I know. I'm
and you're also.
This is always my thing.
I know.
This is my cross to bear. It really is. It's like it's not even a trigger point anymore. I'm just accepted my reality. This is my reality. It's talking about this all the time and constantly giving the same. Yeah. I know it's not your fault.
Yeah, it's not your
we're
fault,
sort of
Manoj.
Teasing Manoj. I'm not trying to be. We're going to answer your question.
Yeah.
It's just this is a question we get a lot, and I know why, because it's a very popular kind of a technique.
Yeah.
Let me give my little couple of slides here.
If we don't accurately answer your question, don't worry. Just the last five live streams, we've certainly discussed this.
Yeah, it's been something that is discussed of a lot. So yeah, let me give again. I'll sort of walk through. These are slides from my RDE webinar. Mm-hmm. It's on our YouTube channel on the members section. I'll kind of go through this. So Tafel analysis, and this will lead into my answer as far as what do you do with the potentiostat. So I do know your question, Manoj. I will get to it, but to give background information as to what you would do with the potentiostat and why, it helps to know where the Tafel slope and the Tafel plot comes from. And so it comes directly from the Butler-Volmer equation. And the Butler-Volmer equation is an equation that describes kinetic current as a function of overpotential. That is what it describes. This is the Butler-Volmer equation. Its current is equal to the exchange current density, which is the heterogeneous rate, basically related to the heterogeneous rate constant. And then there's an exponential where this eta, it looks like an N, eta here is overpotential, which is the potential respective to the E0 of the reaction you're studying, okay? What we do is we take a large enough overpotential, positively or negatively, such that one of these terms can be mathematically neglected. Usually the amount is about 100 to 120 millivolts in that range. It means that you have roughly, theoretically speaking, 99%, 1% breakdown of like the oxidation or the reduction pathway. So it's largely irreversible. Okay. So what we are left with when we have a large enough overpotential in either direction is half of the Butler-Volmer equation. The Tafel equation is half of the Butler-Volmer equation. They are one and the same. So I've put a K subscript here to indicate that this is kinetic current, but it is the Tafel equation in a nutshell. And so what we do with the Tafel equation is we don't usually look at it in this form. Okay. We take basically the logarithm of both sides to solve for the overpotential. And so when we solve this equation mathematically, algebraically for the overpotential, we get this. This is the Tafel equation as it's more commonly used or depending on the textbook, you find the form or the constants. Sometimes there's a number here. 1 over log of E is like 2.5 or some number. So sometimes you'll see a number 2.5 RT or whatever, 2.1. I forget the number exactly. It's irrelevant. This is the Tafel equation, and the Tafel slope is all of this stuff, which comes from the plot of overpotential versus log of the current. That's why you have a slope of millivolts per decade, because it's decade of current, because we have log base 10 of the kinetic current. Now, again, remember that this is kinetic information only, and that's where the Tafel slope comes from. Now, back to your question.
Oh, I minimized it to make space.
No problem. Yeah, I was finding it as well, just to remind myself. How do we do this? Well, you have a couple of options, keeping in mind that to make a Tafel plot, to get the Tafel slope, you must be obtaining kinetic current exclusively. So how do I get kinetic information using my potentiostat, you can rotate a disc. If you have a rotating disc electrode, it allows you to isolate kinetic from mass transport contributions to the current. It's a whole. Again, the slides I just showed you are part of a larger webinar where I talk about RDE, RRDE, Levitch, Kotecki-Levitch analysis. These are the kinds of things that people do pretty frequently with rotating disc electrodes, sometimes HER, sometimes ORR, things like that. And so that is a way to get kinetic current. Another very quick way, which is not always appropriate, but many people do it, is that they do basically a linear sweep test around the potential of HER, which is 0, versus NHE, right? That's it's the reference reaction, right? H two protons plus 2 electrons gives you H2, right? That's at 0. So in theory, versus NHE at neutral pH or whatever, when you go to a negative potential, you start generating hydrogen, right? That's the HER. If you sweep very slowly, in theory, you are minimizing the impacts of non-kinetic things. And so sometimes what people do is they sweep at like 1 millivolt per second, or 5 millivolts per second, or some slow sweep rate. And so they get a voltammogram, which is like I versus E. So you have current and voltage data. Well, you can make that into a Tafel plot by taking the logarithm of the current, flipping the axes, and then you have a Tafel plot. But again, that only means something if the current is kinetic current. And so often what people do is they take a sweep, like an LSV, and they assume, rightly or wrongly, that the current is kinetic current, and then take the Tafel transformation of that. And then they get the Tafel. They take a baseline, you get the slope of that plot, and that's your Tafel slope. So very often the answer to your question is that people take a sweep, a linear sweep. And also very often, as I get on my soapbox briefly, is that these Tafel plots are meaningless because that is not kinetic data. It's very difficult to isolate just kinetic data by sweeping. It's a very rough approximation that doing so slowly is purely kinetic data. Because then when you get your Tafel slope and it's not exactly what you expect or what you think or what literature says or what you think it should be, well, is it because your catalyst isn't doing a great job? Or is it because gas is building up on your electrode? Or is it because you don't have kinetic information and your Tafel plot is meaningless? There's a lot of questions there, and they're not easy to answer. So I always like to just mention this to try to be clear, I guess, about the misuse of Tafel plots very often, is that you can do this because unit-wise, you can turn any IV data into Tafel data. Just take the logarithm of the current, then you have a Tafel, quote unquote, Tafel plot. But try to make sure that you can guarantee as much as possible that you have kinetic current, kinetic information, or your Tafel plot is basically meaningless. So I hope that answers that question to some degree. And again, stresses the connection between Tafel and kinetics. It's like my cross to bear.
It's cross to bear.
Forever and always talking about kinetics and Tafel. It's my thing.
So for this next question, I think we may need a little bit of clarification. Naresh is asking, hi, can you explain what actually happened at electrode-electrode interface during charging, discharging, and correlate this with diffusion and capacitive controlled behaviors? So I don't know what you mean by the electrode-electrode interface. Is this two solid metal or two solid conductive interfaces?
Yeah, what system is this? Is this a battery supercapacitor? Is it a 3-electrode system? What's
Yeah, because depending on if it's a battery or a quote traditional 3-electrode system, or you literally just have two pieces of metal touching each other,
there's different answers.
There's a bunch of different things that are happening with relations to diffusion and capacitance and stuff like that.
Yeah.
So Naresh, let us, like, we're happy to answer your question. We just need a little bit more clarification.
Please clarify on that. Yeah, we'll leave that one for now because I agree. It's like we could talk for hours about what's actually happening at an electrode or something. And please clarify the system or some other points of clarification about what you mean, and we'll try to answer it. But for now, we'll sort of move on here.
Yeah. We have Must Shake has a question. In a cyclic voltammogram, the y-axis current, what is ideal? Is it better to
Fix?
fix or observe observe the reduction in oxidation peaks at lower or higher currents? So I don't think that there's a quote ideal current, so to say. The current is just, in cyclic voltammetry, you apply a potential, and the current is just the response to that potential depending on the electrochemical system. So, depending on the electrochemical system, the magnitude of the current that you get will be different. And what those currents represent, and the errors associated with those currents will also change. For example, if you have a lot of solution resistance, if you have very high currents, you're going to have a bigger IR drop, which is bad, generally speaking. Um, but maybe you are trying to measure very low currents, like microamp currents, or maybe you want to measure an amp of current, or milliamps of current. It really depends on the electrochemical system. There is no right or wrong or ideal current axis, like current value for the axis. And generally, if you have an oxidation or a reduction peak, they're just in different directions. We usually use the IU-PAC convention, where positive current refers to an oxidation reaction, and negative current corresponds to a reduction reaction. And that's really it. There's the U.S. or Texas convention, where it's flipped. Positive current refers to a reduction reaction, and negative current corresponds to an oxidation reaction. And the x-axis values are also flipped. So there are things like that, but I wouldn't say that one is ideal and one's not ideal. I would say it's just whatever your system is, without being any more specific. We can't give you like a more specific answer as to what's good or bad. So you're more than happy to elaborate a little bit more on that, and we can help. All right. So moving forward.
Yeah, I was just doing
Mhm.
his to follow up on his thing. He was trying
Oh
to.
yeah.
He's using a pseudo-reference electrode as low frequency. Yeah, That's the drift issue, right? Of course, is as you get to lower frequencies, um, the pseudo-reference drifting kinds of issues get more and more severe because the low frequencies take longer. It's an unwinnable problem. I mean, honestly, not to be defeatist here or anything. It's just, if you have to use a pseudo reference for whatever reason, it drifts, especially at longer time scales, and lower frequencies take longer. So you're completely at the mercy of like physics here. So yeah, I totally understand the situation you're in. I guess if nothing else, I can commiserate with you, even if you are screwed, I guess. But yeah, so yeah, I definitely understand the situation that you're in.
All right. Let's see.
So Shazaib, I think, is next.
Yes.
So I performed scan rate. I assume like a CV study or something. The process came to diffusion control. Can you guide me how to explain this result properly using square root graph and the logarithm graph of scan rate? Didn't we had a similar thing last week? I think I was talking about Randles-Sevcik, I think. Do we have it?
Yeah, maybe. I mean, we can. I don't know if it's the same. Oh, like a previous question?
No, I just mean like last week there was a thing. I should make sure I give the right answer here, but like the Randles-Sevcik, where is it? It's in here somewhere.
Yeah.
So like, for example, he's talking about like a square root graph
Yes.
with scan rate.
Yeah. So you would plot the peak current. So what you would do, we need to just show like some sample voltammograms.
Yeah, if you want to, I can just hide this. I was just bringing up the equation there.
Oh yeah,
for good measure.
So if you had, say, a bunch of sample voltammograms, a couple things to think about when you're doing this. I'm just going to draw a few small ones. So you're going to have, let's just say you have this as your CV, and this is at 1 scan rate. This is like, let's just call it V1, 1, and then we do the same thing, and then we get this, kind of higher peak, and and then this one's like V2, and then you keep doing this. You keep getting higher, larger and larger scan rates and stuff, and this one's like V3. So there are a few things to note. One is that you're going to have some background current. Sorry, I'm not very good at drawing these CVs, but let's say if this is 0, you have background current here. So this peak current, which is what you're looking for, this guy here, this little peak current, that's your IP, right? And it's also only this direction. It doesn't work for this. It doesn't work for the reverse wave. So this is your peak current. You need to subtract your background current. So you need to subtract background, let's just call it IB. You need to subtract the background current for it. And you need to do that for every scan rate that you're doing this at. But once you do that, once you have your resultant current, I'm just going to call it IR, then you can make a plot of the square root of the scan rate based on the Randles-Sevcik equation, which we'll put out in a minute, and then the peak current, and R, so it's the background subtracted one, and you should find that you get a straight line, or that you have you have data points here because you're doing them at specific scan rates, and this should be a straight line with like a linear regression that's almost like perfect. And if your electrochemical system is diffusion controlled, it will obey this behavior. You'll see this. The error statistic is like tiny. This should plot a very good straight line, and it's all based on this equation right here. I should have just drawn all these CVs here. But this is what you're looking at. At room temperature, the peak current is related to all this stuff, which is the slope. That includes a diffusion coefficient, but it has a square root of scan rate. And just remember, it's in volts per second, or square root of volts per second. So use volts, not millivolts. And that's how you determine that it's diffusion controlled. If you don't get this kind of relationship, it's not a diffusion controlled process.
As far as the logarithm graph is concerned, that one I'm not sure.
Yeah,
I don't know what. Again, this came up before, and I was confused because I'm like, you can take the logarithm of the Randles-Sevcik equation basically, and exponents become constants when you take the logarithm. Like you can do that. I just don't know the purpose.
What I have heard is, and I don't know the equation, but I've heard that if you take the log of the scan rate instead of the square root of the scan rate, you will observe the it's if you have a surface bound redox reaction. So if you get a linear response with the logarithm of the scan rate, then it's a surface bound.
What equation does that work off of?
I don't know. That's the thing. I've only heard about it, but I haven't. I actually don't know where it comes from.
Yeah, that one I'm not familiar with.
But hey, if you have like self-assembled monolayer chemistry, then that would be the equation you would use, because your voltammograms would certainly look very different when that happens.
Yeah, I think I think sort of finding the theory behind that would be helpful, because I don't know.
Yeah.
But
yeah,
it was probably, like you said, something where you'll observe different voltammetric differences based on scan rate, and it might guide you towards making one plot or the other. If Randles-Sevcik peak versus square root doesn't end up linear, then then it's not diffusion controlled, it's surface controlled.
You may have some
whatever
surface bound stuff.
Yeah, so it can indicate a different plot is warranted, I guess.
Yes.
Interesting.
Yeah.
All right, so Saktipada from IIT Bombay is here, and they said, what should be the ideal concentration of supporting electrolyte? Or if we added excess supporting electrolyte, what happened? It depends to a certain extent, like aqueous or non-aqueous. Um, you know, I guess let's just say, sort of as a general rule, if you have aqueous electrolyte and 3 electrode kind of systems or whatever, um, something like 0.1 molar for like most typical salts is usually like plenty concentrated enough for like successful electrochemistry, right? As a general rule, I mean, it can vary, of course. Like in non-aqueous, usually that number would probably tend to be higher. What you're after ultimately is to lower the like uncompensated resistance basically as much as possible by having and to minimize things like migration effects or whatever by having a substantial electrolyte concentration. Um, and it's also solvent dependent. So like things like water or acetonitrile have a relatively low, like, with decent electrolyte concentration, they have pretty low impedance and, they perform well. Things like DMSO or DMF or THF have like a really high, even with high electrolyte concentration, they just have a really high impedance. So it's solvent dependent. As a general rule of thumb, it's like, I don't know if I had to put numbers to it, because I know practical answers are helpful for people. It's like in aqueous solution, if you have like 0.1 molar, like KNO3, KCl, sulfuric acid, KOH, like all of that is going to be like from the amount of electrolyte perspective to minimize like IR drop and things like that. That's like a lot. It's plenty. It's more than enough. You don't have to go to 0.5 and 1 and 1.10 molar. 0.1 molar usually, or 0.5 molar in that range is like more than enough. With non-aqueous, you're talking, it's like one order of magnitude higher. Like battery electrolytes, you'll do 1 molar, like lithium something, or lithium chloride, or lithium PF6, or whatever, or like what's the main one, like TBA PF6 or whatever. And that's like the typical sort of supporting electrolyte. Usually you'll try to do like 0.5 molar or 1 molar if you can, or something, and then you have a small amount of ferrocene or ruhex or whatever you have. But like the supporting electrolyte in non-aqueous, you want it to be higher to overcome some of the limitations of those solvents that I was talking about. So I don't know, that's about all I can kind of say. What happens if it's really high? I mean, generally speaking, you're not going to cause any problems by having too high. I suppose something weird might happen if you like ridiculously concentrate. I don't know. I'm just guessing. The problem comes more on the other side when it's really low, right?
Yeah.
When it's really, really low, you can have really high IR drop and distortions in your voltammograms and stuff like that. So.
Yeah, when you have like really, really high supporting electrolyte, if it's like saturated, then it could crash out of the solution.
Yeah, I guess
it's like more of a physical.
Yeah, you'll have
thing.
like precipitate at the bottom, which if it's not near your electrode, it doesn't probably matter.
Yeah.
But I mean, if it's like if you're rotating and you have crashed out stuff and it's like hitting the electrode, you'll probably get weird data. Like, there's some things that could happen. But for the most part, you can consider that probably really high electrolyte concentration is not going to do you any problems.
Yeah.
It's not, it's there to reduce the IR drop and reduce migration and make everything happy.
Yes.
I guess. I don't know.
Yeah. He has a follow-up question, which is for homogeneous solutions, how to potential window, and what would be the scan rate to assign of a peak. So to determine the potential window, which I think is what you're asking, I always recommend that people.
This is your cross to bear. You answer this question.
Yeah, I don't know why.
For me, it's Tafel, and for you, it's potential window. I'm not sure why.
Yeah, I don't think it's. I mean, I think both of us can equally answer.
No, I know. It's just funny.
One.
It's like these are the questions that we
default to.
They haunt us in our sleep, I think.
If you're doing like a potential window and you're just trying to figure out where it is, I think the best thing to do is to kind of like, if you're at 0, just like do sweeps back and forth, and then look to see if like you get any meaningful change in the current. So sweep a little bit and then sweep a little bit, and maybe this is your first experiment, nothing happens. But then maybe the next time you go up and it's like it goes up a little bit, and then you sweep down and it goes down a little bit. And so you're like, maybe that's about it. But you may sweep further and it's like, oh wow, okay, all right. And then this happens and it's like, okay, I really know that realistically from here to about here, maybe even here, is my potential window. I can only effectively do electrochemistry of new molecules within this range. And when it comes to the scan rate that you need to, actually that's for picking a peak. Sorry, this is how you would empirically determine. I don't think I was speaking to the camera, into the mic. This is how you would empirically figure out what your potential window is, because your potential window is made up of so much stuff. It's made up of the solvent, electrolyte, um, electrolyte, and then it's based on the electrodes themselves. So anytime any one of these things possibly can degrade or change or induce a reaction, it's a limitation. So sometimes like this, if this is water, this is like, water's breaking down. We're reducing water to protons or converting water to oxygen. And so there are these other reactions occurring that limit the potential window that you can work in. So, and in some things, if you had to say like a copper, if you had a copper electrode instead, it might look something. It might look something like this, because like, copper oxidizes really really quickly, and you have a much smaller potential window, right? Or maybe this is actually extended further out because you don't reduce protons to hydrogen until you hit like much more negative potentials on the copper electrode. So this whole thing can kind of like shift around a bit. So, but to determine it empirically is the best way, because doing the math to kind of, and looking up every single solvent, electrolyte, electrode, and window about what reactions are occurring might be very difficult. Still, it's good to know what you're working with. It's good to know what these things are and have a general sense of them. But yeah, it's a little, unfortunately, trial and error. But once you know what the window is, you're good. And then your last question. Let me see. What was it? Scan rate.
Scan rate, yeah.
What scan rate to assign that you should use to assign a peak? So ideally, your peak shouldn't really shift around too much. But let's see. So let me just
Depends on the kinetics of your reaction.
Yes. So if you have actually, why am I doing this? Here, let me share. Let's just show people Aftermath, kind of like the simulation software.
Mhm.
So if I simulate a cyclic voltammogram, and let's just say I have like a 1 electron transfer reaction, I'm gonna just add some parameters here, and then let's just look at the voltammogram here. My E naught is 0. I simulate. You'll notice like, okay, my peaks are here, and my E naught is 0, which I've defined it that way. I could shift this around. I can make this, 100 millivolts, and then simulate it, and then this thing moves over. I can make it negative 100 millivolts. So this is how I can move my E naught around, sort of say. So if I just make it 0, we center it. So that's the potential, right? Is E0. Of course, your peak anodic and peak cathodic current is going to not be 0. It's going to be a different value. Going to be slightly more positive on the oxidation side and slightly more negative on the reduction side. But if because my heterogeneous rate constant is very fast, as I go to say faster scan rates, go 200 millivolts per second, it increased the current, but it didn't like shift this around very much. If I keep going, I'm also getting faster scan rates, but my peak potential isn't really changing around a lot. It's only the case there are two situations. If we go back to 100 millivolts per second, if my rate constant is very slow or slower, then you'll start to see that as I change the scan rate, these will start to move away, and my peak position will change. My E naught is still the same. E naught is a thermodynamic quantity, and it's still kind of in the middle between the anodic and cathodic peaks. But if I also have, say, solution resistance, can also cause a problem. So if I add solution resistance, it also creates a peak splitting. It also separates the peaks and gives you a peak potential that's like way, way off. Now, this is very exaggerated. It's 1,000 ohms though. So the scan rate, to figure out what the potential is, you need to make sure that you correct for solution resistance. And it's a little bit hard if your rate constant is very, if it's very slow, then to get an accurate value. And let's just say this was normal. Let's move to a much slower one. Then let's say if you started at 100 millivolts, then you're still kind of, it's a little bit hard to tell these peaks, but you may decide to slow down, and you kind of bring these guys closer and closer together. So if the rate constant is really, really slow, you may have to sweep very slowly. This is 1 millivolt per second to actually, to get a more accurate peak potential position, if you will. You may have to go to slower scan rates, but it's very much dependent on the rate constant. And you can do this kind of experiment on your own. This is Aftermath Live, our simulation software. So it's something that you can purchase to actually experiment with these types of things. It's just a soft marketing, if you will. But hopefully that answers your question about the solution, the potential window, and the scan rate needed for assignment of a peak.
It's very good. Yeah, it's much more effective to use the software than to try to draw. Drawing CVs is really hard.
Yeah, I'm just like, oh, why am I going to do this now?
Why am I bothering? I have software that
I have
draws it
software.
for me. Why would
Yes.
I waste my time? Yes. Hob G has another question. Using ferrocyanide in cyclic voltammetry, if the reduction and oxidation peaks are slightly different, should you average the two peak currents for the Randles-Sevcik equation? So recall what Alex just talked about, not this, before the simulation, you were drawing the, like, you called it IR or something. So this can depend. I suppose I could use, I'll just draw it. I don't know precisely if I can simulate it perfectly well in the moment here. I just want to draw what I mean. If you start off with all one species of ferri or ferro, and I always forget which is which, to be honest, but this is 0, right?
Me too.
so it's ferri CN6 basically, and then is it 2 and 3 or 3 and 4? 4 and 5?
Yeah, it's a 2-3 couple, I believe. Well, actually, no, I
9
think you're right.
plus to 10 plus. I forget.
Yeah, no,
I always forget. It's 2 or 3 or 3 and 4, whatever. Plus an electron gives you the other one. I'm really bad at remembering this, to be honest. It's like, it's so common, and it's just like, it's like 3 plus to 2 plus, or 4 plus to 3 plus. I never remember.
Well, yeah, so that is
it's 4 and 3.
So that's the charge on the iron.
Yeah.
But the cyanide has a -6. So the total charge on the molecule is like -3 and -4 or something like that.
Oh, minus, not plus.
Yeah.
So 4 minus, 3 minus.
But you're right. It's like, well, one's iron 2
whatever
plus,
it
one's
is.
iron 3 plus.
Let's just say you're starting with all of the oxidized species. You have like 100% of this, and you have none of this. What you're going to get is that at positive potentials, whatever the easy, it's like 200 millivolts or something like that.
Yeah,
whatever.
Let's say 200.
I'm just gonna put E0, whatever the E0 is. It's around 200, I think, but it's irrelevant at this point, just for argument's sake. So what it means is that at potentials positive of E0, I'm not going to have any current, basically. I mean, I'm going to have slight background current, but basically I'm not going to have any current here, right? Because I've already got all of this species. I can't push the oxidation reaction. I've already got it all. So what I'm doing is I start positively. I have zero current. Again, it's not really zero. There's going to be some background current, but just for argument's sake. Then I get close to my E0 and I'm going to get my peak, right? It's going to be slightly negative of that. And then when this levels out, it's going to level out not at zero, because I always have some of this species that continues to reduce. Then when I switch directions, I'm going to get something like this. Okay, it's going to make its peak again just beyond E0. And then this one will be centered closer to zero, because now, and I'm drawing it, it's like this width should be the same as this width, right? Fine. But my point is, don't be fooled into thinking this peak right here is more negative. You know what I mean? Like this might be minus 100 microamps or something. And this might be plus 80. But remember, you want to, it's the difference. So this peak is actually like this distance, right? From the back, it's like you got to subtract the background. And this peak is, you know, there's a gap here that you have to take into account. So now if after all that they are different, right? Okay. So anyway, back to my point here. These should be roughly the same within some experimental error. I mean, they're not going to be exactly the same number, because like this is science. Nothing ever works perfectly, but keep in mind to like subtract the background. Again, taking into account that whichever species you start with, sometimes people use 50-50 mixtures of it, and that's a whole thing. So, but if you subtract the background current and you get a true peak, like, you know, background subtracted peak, they should be roughly the same. Now, again, if they're not, you can take an average of them. That's a possibility. Sometimes people will pick just one. So for example, what I would maybe do in my case, if I was advocating, is because I'm starting with all of the oxidized species, I would probably just use the reduction peak, because it's, to me, it feels like more accurate. I have all the oxidized species. And so the reduction peak is more like, it's 100% this reaction. That to me, like I'm starting from zero and then I have the peak like that, to me feels like the more accurate.
Oh, that's like 100% correct.
Yeah.
The Randles-Sevcik equation does not apply to both peaks. It only applies to the one where like you start with the oxidized form, like 100% oxidized form.
Okay.
You reduced it. The peak from the oxidation would not work with the Randles-Sevcik equation.
So it was even more firmly that way.
Yeah.
My intuition was not just like a decent suggestion. It's actually
literally correct.
So that's good to know. Okay. So then, yes, definitely use that one.
Yeah.
But I have seen instances for example, it's not exactly the same. It's not Randles-Sevcik per se, but like when people are doing the ECSA on the platinum hydrogen thing, hopefully if you know what I'm talking about, but like you have the hydrogen desorption and the oxidation part, and you have the hydrogen adsorption and the reduction part, and you get the area under the curve of both of those, and that's how you calculate the ECSA of platinum, for instance. Sometimes what people do is they average those out, because it's like they should be the same, but they're not really. And it's like you could do the same kind of thing where, like, in theory, you should probably just use the reduction one, because that's the adsorption. It makes more sense than like how much was desorbed. Like you shouldn't use the desorption because you're starting from nothing, and then that makes more sense. So but sometimes what people do is they get like, like 200 microcoulombs here and 195 here, so whatever, it's 197. And you average it. Like there are some styles where you can do that to sort of get an aggregate or an average or whatever you want to call it. But based on what I did just talk about, I guess you do really want to focus on the minority and majority species to guide you as to which one to use for the Randles-Sevcik.
Yeah, absolutely. All right, moving forward.
Saktipada has another question. Did we get to that? This is a new one. Is it a continuation from the other one or not? Or is it for reduction? We use negative potential, oxidation, positive potential window, I think. Is really change the energy of the electron of electrode, or is it band energy related?
Wait, what is this?
So for reduction, they use a negative potential, oxidation, a positive potential.
Yes.
Is it change of the energy of the electron of the electrode, or is it band energy related?
Oh.
It's
this
more
is
of a,
this is this
this
is like
is right up
this
your.
is like my favorite subject.
I know.
So in a pure conductor, like glassy carbon or platinum or something, when you change the potential, you are changing the quote Fermi energy of the electron in the conductor. So it's relatively direct. It's potential and so there is no like so yeah, it is weird to think of it as band
It's not
energy.
really in a conductor. The band, like the band, there's no band.
There's
Well,
no band gap.
yeah, there's no band gap.
It is a there's a continuous band, but the band is not full, if you will. Like in a semiconductor, you have a, let's just say, what you would see in most books is that you have a completely full valence band,
Mhm.
a mostly empty or
Conduction band.
conduction band, nothing in between. That's your band gap, and the Fermi level is right in between.
Yep.
In a solid conductor, you have a full complete band, but it's not completely, sorry, you have a band, it's not completely full, and when you change the potential, you are changing the relative energy of all the bands simultaneously. Um, so when you change the potential, you're moving those bands up and down, but the relationship, but like the potential is not equal to the energy, right? So if I change it by some amount, it's not equal to the energy. The thing that relates those two things is the electrochemical potential. So electrochemical potential is the thing that relates the energy of your metal to the potential or the energy of the electron in a metal to the potential that you apply. So that's the thing that bridges those two things together. I hope that answers the question.
Yeah. This is
Yes.
like our endless conversations about Mott Schottky and semiconductors
Yes.
and the band energy and all of this. It's a very
And
long.
and for a long time, like I was just trying to figure out like what exactly, because here's the problem that I think a lot of people have is we have this band energy diagram that you see in these books, but you also see the electrical double layer, this graph of like phi solution, phi of your electrode, and then
It
the drop off.
drops. Yeah.
And it's like, well, that energy? It's not energy, it's potential.
Mhm.
But you're ultimately trying to deal with like a delta G, some kind of thermodynamic energy, but you're not changing the energy, you're changing the potential.
Yeah.
But those two things are not exactly directly related. And the electrochemical potential is the thing that relates those two things together. So we'll just leave it at that unless people want to know about that, which maybe hopefully they don't.
Yeah.
I mean, if they do, we can talk about it.
Talk about it forever, but I'm not sure that it's the most interesting, frankly.
It is the most interesting thing.
Depends on who you are.
It is super interesting
to you, not necessarily to everybody.
Yeah.
You know what else is interesting? How electricity affects water.
How does electricity affect water? How does electricity affect water?
I think electricity makes water feel very uncomfortable.
Yeah,
You know?
very uncomfortable.
Yeah.
It's not in a best place, kind of physically and mentally.
It's working on itself.
It's working on itself.
You know,
It feels
very unwanted.
kind of, yeah, it feels
know?
unwanted. It feels, its pH is changing a little bit sometimes.
That's right. It's
That's
a problem. Yeah.
Feels a little gassy sometimes. Not very comfortable.
I think electricity is gonna recover just nicely. Yeah. I guess I don't totally understand this question. How does electricity affect water? I mean, like it takes a lot to get electricity to go through water. Like, the classic example, right, is like, be careful when you're in the bathtub with like a blow dryer or something, right?
Mhm.
And that's because water that comes out of the like tap is not really water. It has electrolytes in it. It has salt in it or whatever, right? And so that conducts And if you have a high enough voltage,
Yeah.
basically, right, which is like something out of the wall there's a lot of
Yeah,
voltage
it's a lot of
there.
voltage.
If that voltage touches the water, it can bridge the gap between something else, which is your body,
Hmm.
and then you get electrocuted. So, in general, though, with as it relates to electrochemistry, because that's where you are, is a live stream about electrochemistry.
Yeah.
Um, Electricity doesn't go through water ever in electricity in electrochemistry. That's not what happens, right? Um, when you put electrodes in water and you do electrochemistry, the electricity, which is the movement of electrons, occurs externally. Electrons do not flow through the water or the electrolyte or the solution, whatever you want to call it. That's not what happens. The flow of charge in solution occurs ionically, with ions, not with electrons. It takes a really high voltage, a really high energy difference. Not the same thing, I know, but it takes a lot of energy to
Yeah,
push
yeah.
electrons through water. They go through wires, they go through metal, right? Very easily. They go through
Mhm.
water, it takes a lot more energy, it takes a lot more potential, it takes a lot more push. And then they go through air, takes a lot of energy, like
Mhm.
like teravolts. That's what lightning is.
Yeah.
In a thunderstorm, that's what lightning is. It's electricity with so much, like, potential behind it,
Yeah.
that the electrons move directly through the air, because the air has humidity in it, and there's some ions in air, like,
Yeah.
not a lot, but some. And so, if you have a huge amount of potential, basically, you can drive electricity directly from the clouds to the earth, and that's what lightning is. But basically, it's like air, liquid, metal, something like that. It takes a lot of energy to move it there, and basically, metal is the thing that we're using. That's the wires, the electrodes, the clips, the potentiostat, all of that. That's what we're doing in electrochemistry.
Mhm.
So, not sure if that's
Yeah.
exactly what you were asking, but that's my answer, I guess. So, yeah. Um, Naresh
There's-
had a follow-up, but I'm still waiting to see what system they are referring to. They're
Yeah.
saying electrode electrolyte interface. So, maybe the question is generally like what happens at the electrode electrolyte interface,
Yeah.
as it relates to diffusion and capacitance and things like that. I guess I just want to know. Do you mean
Because
you
it's
said
different.
charge discharge? That's why I'm kind of
Yeah, because when you say discharge discharge, it's like that's usually a term that's meant for a battery.
yeah, or a capacitor, I guess. But
Yeah.
so I mean, the answer can depend on those processes. I guess that's why I'm sort of waiting here.
Yeah.
But anyway, so we can kind of
Yeah.
wait on that there. Yeah.
Yeah.
So
Wait a little bit before we talk about that. Uh let's see.
where do we? Oh
Um
yeah. So Saktipato is. I always struggle
yeah, we can show the
with the process. I'm not sure if there's a question or just a comment. I guess I
yeah.
struggle with the process, how energy changes the electrode. What happened in the instrument?
Oh, yeah, yeah. Yeah, my belief or understanding is that I don't know what the what the instrument is physical like. I understand how a potentiostat works, but I still use the words like potential here, voltage there,
Mhm.
current there, but like fundamentally I don't know like how exactly, the power amplifier is moving potential or
Yeah, like
something
physically, what's it doing?
physically what's it doing. But what the instrument in my understanding is it when we say the working electrode potential is changing, we're taking the band of the conductor and we are moving it. We're moving all of the bands collectively up and down. So if it's negative, we move it up. When it's positive, we move it down, on an energy scale. So that's what the instrument is actually doing, um, to affect things. You're not actually changing the energy level within a band. I think you're changing all because that
Mm.
means you have more or less electrons, and I don't think that's happening. So, but yeah, and that's what the instrument I think is fundamentally doing. to the electrode in your system. Okay. We did hear back from Naresh, or actually, we do have a question from Habji.
Yeah.
Just came in. So Habji is asking, now is the charge being transferred by the anions or the cations? That is a very good question because there is something known as the transference number, and it is the idea that depending on whether you have, because for example, you may have, let me see. If you have a molecule that has like a 2+ charge, for example, I think what like zinc chloride or something. Zinc is 2+ and chloride is 2Cl minus. So the charge is balanced. But you have two single anion. Let me draw this so that at least kind of it's a little bit easier to visualize. But if I had, say, and I don't understand this completely in terms of how to calculate it, but the transference number is if you have a molecule, and I don't know if this is a real molecule. If you have zinc, and then you have Cl minus, and then you have Cl minus, the charge is balanced, right? I have two positive charge and two single negative charges, but the ability to transfer charge is fundamentally different between these two. If I just have Na plus and Cl minus, it's easy to say like, oh, well, this guy carries the positive charge, this guy carries the negative charge. But here, it's a little bit different. And so the calculation of the transference number actually looks at, say, the charge. It looks at something like the charge, which is indicated by like a Z. It's like the number of moles of the thing. So in this case, chloride's 2, but
Problem
it
is
has
Z
1.
and you've just written zinc.
Yeah, which
You're
which
trying to write
I'm
something
trying
else.
to write something else.
If you
and I just
picked
wrote
any
zinc.
other element, you would have been fine, but you picked zinc.
I picked zinc.
Put vanadium or something. I don't know. It's like
vanadium. Yeah,
You're
well,
like, Z and
then
moles.
N and
You
moles.
picked zinc. It's like
Zinc.
just the worst coincidence.
Let's just do this.
I don't
Yeah.
know. That's so funny.
So Z,
Sorry.
so Z is the charge, and then N is the number of moles.
You literally wrote zinc. This is like funnier to me than I think it is to anyone else, but I just find this hilarious.
Yeah, and
so
then on top of that, I'm like, oh, if you take the peak current and then you subtract it from the charge rate, well, that's a result. So let's just call that IR. And I'm like I definitely should not have called it IR.
Oh my god. That is so nerdy and so funny. I can't even. I'm sorry.
So this is for the positive one, and then this is for like the the negative ones, and there's some transference number that is associated with like maybe the chloride carries the charge as the anions or the cations. So that's ultimately to say I don't know the answer, but it's also to say that it depends. It's not always clear what how is charge being carried via ions and cations. But when the current is measured, really, when we measure the current, one of those two tends to carry the charge a bit more. So, but yeah, that is that answer. Let's see.
So we can maybe get to Naresh's.
Yeah, because he's talking about supercapacitors.
Yeah, so supercapacitors. So the original, I have to go back right here. The original question was
he wants to know fundamentally what's happening at the electrolyte interface during charging and discharging related with diffusion and capacitive control processes for a supercapacitor.
Well, what I can show is my cool little animation. Where the heck is it? It is in like my second webinar series. You probably have one too somewhere, but
of double layer charging.
Yeah, just showing it. I could show the little. I mean, it's kind of what's happening in the very in a very rudimentary way, if you will. But it's for the purposes of kind of trying to explain this. So one of the answers here, and I mean the reality is quite a bit complex, but I guess for the sake of just understanding and learning here, what is basically happening at a supercapacitor is that you're forming a double layer at the surface, and that's where the charge transfer happens. And so, what at the solid electrolyte interface, it's non-Faradaic capacitance, which hence supercapacitors. And this is actually part of a slide of one of my webinars where I talk about this isn't very much good. It's not wanted except for supercapacitors, which is what you're talking about. So it is a good thing in your case. So you can think about it as an electrode and an electrolyte, right? So I'll have water, for instance, as a solvent, and then my electrolyte. In this case, I just put KCl, right? So I have positive potassium ions and negatively charged chloride ions, right? Roughly in some concentration here. Okay. During the charge discharge processes, I'm either applying a negative or a positive, polarization to my electrode. And so effectively what is physically happening to some extent, I suppose, is that if I apply a negative potential at my electrode, well, negative will repel negative and it will attract positive. And so the negatively charged ions will be repelled from the surface and the positively charged ions will be attracted to the surface. And so what I'm getting and why it is called a capacitor is because it forms in a microscopic way this kind of phenomena where I'm lining up in a plate or a plane of positively charged ions close to the surface, and my electrode is negatively charged. And so this is quite literally definitional of a capacitor, which is two oppositely charged plates that are some distance away from each other, separated by a dielectric material. And in this case, the plates are the electrode and solvated ions, and the dielectric is the solvent, which is water, basically. And so there's a lot more to it. Like it's actually like there's an inner Helmholtz plane and an outer Helmholtz plane, and then there's the potential drop off over distance. Like there's a lot there, to be honest, that I don't know how deep we really need to get per se, but that's kind of the like rudimentary way you can think about it, is that polarizing the electrode is just lining up solvated ions at some distance from the surface. That's the capacitive behavior, basically, in a very simplistic cartoon, I guess. Do you have anything more intelligent to add?
No.
That's like a very simple.
Yeah.
You
That's I guess the simplest like description of it. And I mean, there's a lot of also keep in mind these are just cartoons that we draw. When you actually think about like atoms and molecules, some of them will be irreversibly absorbed onto the surface. Some of them will have that solvent in between. The orientation of the solvent molecules will also be a little bit different because if it's water, for example, water is polar. So when it's negatively charged, the positive protons on the on water are going to be oriented towards the surface. So like there's a whole structure, if you will, of there's kind of this big structure, if you will, that forms, and there's many people who have described this structure and how complex it is, and that and there is a potential associated with that, right? And what's that potential? It's the potential difference between the the charge on the metal, or what we will call like the phase of the metal and the phase of the solution, and that creates the potential difference, if you will. And then as you change that potential difference, more or less charge needs to be added to either side. More more charge on the working electrode and then more charge via ions to meet the potential that you set the potentiostat or your supercapacitor to. And if you run out, for example, if your supercapacitor can't support that much charge, then it won't have a high voltage or anything like that. It still uses the same equations, that the voltage is equal to the charge on a capacitor is equal to the capacitance times the voltage. So to have more charge, or to have a higher voltage, you need more charge depending on what the capacitance value is. So there's a lot of stuff, but I think that's the the
Yeah.
gist of it.
If you
Really.
need clarification about any specific part of that, just let us know, I guess. But
Yeah.
we'll move on for now. So, Saktipada, you asked how to contact us. You use Autolab and Biologic, but you have our RDE.
Mhm.
So we have a rep. They're in Mumbai and also Kolkata. So Batsal, you might be familiar with them. I gave you our email address, so you can email us that
Mhm.
as our sales email. You can reach us if you'd like directly. Most equipment purchases you have to use our representative. But Aftermath, if you want to use the simulation software, it's actually you can purchase it. You can purchase it yourself. This is the website. It's actually directly
Mhm.
online. So it's called aftermathlive.com. So I don't know if you can see the URL, but this is the website, and you can compare editions and buy. You can buy a license directly. There's three options, like student basic and research options. You can see what are available there. I have to sneeze.
Yep.
Oh, it's not.
It's
It's going to come back. I promise. It's not good. Okay. So you can come here and purchase it directly yourself. We also can sell licenses. Um, you know, uh, like we can send a license, but the most sort of preferred or convenient way, I guess, is directly through the website that you can access the simulation.
Mhm.
If you don't, and if not, you can purchase like we could send a license file for Aftermath and stuff. But
Mhm.
mainly it's the online platform is where you can purchase a license and use it directly in on your own computer, Mac or PC, or on your lab computer, as long as it's internet connected.
Mhm.
So that's where you can get to the simulation. Okay.
Uh,
So Dooley has another question about
yeah.
drift in a non-aqueous, basically.
Yeah. He says, not sure if you've answered this in the past, but if you haven't, can you explain what drift is? Is it the buildup of ions around the pseudo-reference electrode? Question mark. So he's talking about
Like,
drift specifically with regard to a
yeah,
pseudo-reference
like what we
electrode.
always say this. I actually don't think we've ever really that I can remember. Maybe we have. It's been 91 episodes or something. So I feel like we've probably answered everything, or admitted that we don't know the answer to everything.
Yeah.
But that is a good question. Like we talk about this all the time. When you use a non-aqueous reference electrode, it drifts. The potential drifts, but
Yeah.
why? I mean, I suppose the answer is
The Nernst
it's the
equation.
Nernst equation. Exactly.
Generally speaking.
Yeah. So the answer is probably tied to the Nernst equation in some
Mhm.
way, where it's like, is it the buildup of ions? Like, I mean, what exactly does that mean? What ions, whatever. I mean, my thoughts, I would say, are things like, different passivation layers or different ion buildup or different sort of unknown processes are happening at the surface that who knows precisely what it is, because it's not pinned by a known reaction like silver to silver chloride, which like is a fixed Nernstian potential. And so if you have unknown processes, what are those specifically? Again, I'm not 100% sure I know, but whatever they are, they have different activities and concentrations. They have different thermodynamic potentials associated with them. And if the concentration, how, why, I don't, again, I don't totally know, but you could just imagine the Nernst equation. You have RT over NF natural log of Q. Well, Q is the concentration of reactants over products. And if one of the reactants or products is some surface bound thing that's becoming larger in concentration over time, the potential will start changing because of the Nernst equation.
Mhm.
Something like that. But yeah, like
Yeah.
specifically what it is, I don't know. I mean, that's kind of
Well,
the point, is because it's unknown, it moves in an
mhm.
unknown way,
Yeah. I
right?
mean, if we think about just like measuring the open circuit potential, the
Mhm.
open circuit potential changes. And I think another thing about drift is it's happening at the low frequency
Mhm.
regime. So we're also talking about time scales where just like we allow the system to just be for a very, very long time. Sometimes, you know, uh, if something happens so fast, in like the high frequency or even mid frequency region, it doesn't drift because you're making measurements so quickly. But drift also can occur because it's also being compared to a working electrode that you're trying to hold it at a potential and a subtle vibration happens. Well, on the time scale of your experiment, that's gonna cause a distortion. But if it's a fast frequency, it's like, well, you could be like shaking the thing, very, very wildly, but at a megahertz, it's as if it's standing, perfectly still. So it's kind of like a relative thing. It's like the time
Mm,
scale
yeah.
uh is another element of explaining what drift is. But that's a good question. I've always thought of it as just like, it's a Nernst equation related thing. Like the system has not fully equilibrated
Yeah.
like a
But it's like, what isn't equilibrated? Like
yeah,
what ion is there? I'm not sure anybody really knows, or if they do, I'm not sure it's
yeah,
readily discussed. I feel like it's one of those things where like it's a good question because it's one of those electrochemistry axioms, I would say,
hmm,
that I for sure, and I say we as a community, but I know I can speak for myself, take for granted. Like
yeah,
it drifts because there's unstable stuff, and the Nernst equation dictates that changes in concentrations or whatever, it
yeah,
moves. But it's like, what is it? What species? Right?
yeah, yeah,
This is
yeah.
like the core
Oh
thing.
yeah,
It's
E-core
like we
and
sort of have these concepts down from a practical perspective. It's like, what is it
what
exactly? And it's
exactly
like,
is it?
I don't know how to answer that question precisely. Like,
Yeah,
is it, I mean, it's like silver, right? You have silver wire in solution. Is it like, is it silver oxide? Is it silver carbonate? Is it silver hydro? Like, what
yeah,
is forming at the surface?
yeah.
Is it a silver oxyhydroxocarbolic,
Oh yeah.
species that grows in length, and that's why the change is like, I don't know any of this. I don't know specifically what it is. I
Oh
just
yeah.
don't. I say passivation layer all the time because I know that's a process that happens in corrosion, that happens on
Mhm.
steel. Stainless steel, for example, has a very, passivation layer. The growth of a passivation layer over time can make getting an open circuit potential reading on steel really difficult. But what is that pass? I have no clue.
Oh
It's
yeah, yeah.
it's a layer that's passivating. Like I don't really know what it
Yeah, I don't
is.
know what
Like
it
I don't
is.
know what it consists of. I really don't. I just know that it's a thing, and I know practically what it sort of does. But yeah, it's a great question because it's
Yeah.
like, what is it specifically? I really don't know. I don't know that I could tell
I
you like chemically what it specifically like. It's like the SEI. I know somewhat what that is, but nobody's
yeah.
100% sure either.
I also feel like drift, the working electrode also plays a little bit of a role too.
Yeah, for
Maybe a
sure.
bit.
Because now you
Because
have
then there's
I
you
mean,
have
it's
two
like,
things that could be changing.
yeah, and you're always looking at the difference, and none of them are anchored anywhere. So
Yeah.
it's just like anything swimming around. How you supposed to?
Yeah.
It's like
Yeah.
nothing is anchored by chemistry
Mhm.
that is unchanging, like the AgCl or calomel or whatever. Right?
Yeah,
That's why I reference
ideally.
electrode. Yeah, exactly. Ideal non-polarizable kind of couple. That's a good question,
Oh
though.
yeah.
Yeah, it's a really good question. You've sort of put your thumb onto a topic that is more often answered practically and not theoretically. It's a great
Yeah.
question, though. This is where I feel like I'm betraying that I'm not an academic. I'm not an academic. I'm an industry, right? And so
Mhm.
my if you ask a professor, they'll probably talk for 45 minutes about something, and you'll get a class lecture, and maybe you get the answer, maybe you don't. And for us, it's like, well, here's how to do something practically because you just want to get results. But I don't
Mhm.
know why that's happening. Like,
Yeah.
I go more to the practical most of the time, but it's a good question.
Yeah.
This next couple of questions I can kind of answer together because I have the data
Yeah.
from last time.
Mhm.
So Saktipada had asked two questions. Can you explain about the foot of wave analysis of CV? How do you do analysis? I did this last week or the week before, but I can show you again
Mhm.
here. And then can you simulate Autolab data using the Pine simulation software? So um, the the direct analysis of this question is a bit awkward. Can you simulate Autolab data with Pine? Like, what do you mean simulate Autolab data? Like, if you're trying to if you collected like a voltammogram with Autolab, can you simulate it with Pine? Like, yes, but the I think the wording of your question is a little bit strange to me. I'm not sure I fully understand. But let's just pretend you got this CV curve in in Nova, right, in Autolab. And what you want to do when you simulate, for example, with our software, is determine like the kinetic parameters or something, right? So what you can do, for instance, is you would input the data into our software first. You would need to get so from Autolab, like our software can't load Metronome files. Similarly, their software can't load Pine files, right? But you can usually get like the
CSV or the text file.
Exactly, the text data of voltage and current or whatever. So most softwares allow you to get that kind of tabulated. So you can input it into our software and you get that. Now what you can do is do like a comparison thing. So I can kind of try to simulate this very quickly. But what you do is, okay, so that's my plot from Metronome, right? And let's say I want to simulate it. It's probably a simple like E reaction. I'm just working through this very quickly. It's probably like 400 millivolts, roughly speaking. Honestly, I have no clue what the K is, but it's relatively fast. It's probably relatively symmetrical. I have no idea. -5. Probably, whatever the diffusion coefficients are. Like all of these things are things you would have to sort of know about your system. So I'm taking all of this for granted here. Let's see, probably 2 segments starting at -3000, going to, I think, 1, back to -3000. I don't actually have any idea what the scan rate was of this data. This is someone else's data. Oh, that should be 1000. Let's just do this. Let's just see what happens. All right. So it's because I've got this initial little thing here. Let's just kind of zoom in. So you can see I'm way too high of my peaks. I could either try scanning slower. I could mess with some of the parameters a little more. It's like way too high still. I don't know if this.
You have like 100 millimolar.
Yeah,
it might be like 1 millimolar.
Yeah,
a bit closer.
Yeah, I think you're right. Yeah, that's kind of so.
It's a little bit better.
So yeah, I mean this. Okay, I'm not going to go any further just for the sake of time. The point here is that this is what I'm illustrating to you is kind of a process by how you can do this kind of simulation here. It's like eventually I would adjust my parameters enough, like, oh well, is this diffusion coefficient too high or too low or something, and that'll help me narrow down to get this curve equal to my Metronome data or whatever. And then I could, when I get it to match pretty closely, it's like, oh, and there's so many parameters to work out here that it would take you some trial and error or whatever, right? But it's like, oh, well, if I know what the diffusion coefficient is in theory of my system, I can narrow down the parameters that I need to kind of, adjust to get my answer or whatever. So, so that is kind of how this might be operated, for instance, and that's sort of the answer. And then the other part of your question is foot of wave analysis. Again, I did this last week. I'll kind of step you through it again. Effectively, the theory of this analysis is to do Tafel, basically. And so it's back to my original point here, which I'm stuck answering this for my entire natural born life. I've accepted my fate. The reality is that it's not necessarily appropriate. It's not necessarily the correct kind of thing to do because, again, this is not purely kinetic data. When you're doing a cyclic voltammogram, and if you scan really slowly, you can kind of pretend it's whatever. But the point that you're doing is that right here at the foot of the wave, right? So select points. So like right where the current starts to uptick and increase basically exponentially, this data right here is kind of like the Butler-Volmer equation, where there's an exponential increase. And so what people can do, and they do, is this foot of wave analysis, where you sort of make the assumption that this part of the data, where the current initially increases basically pseudo-exponentially, is kinetic information that we can get Tafel information from. And so that's kind of not really perfectly correct or accurate in all cases. In some cases, maybe it is. Again, maybe I should just leave that there again, because I'll talk for like 3 hours about this thing. It's like my cross here. But what you would do is take those data that are roughly exponential, assume, hey, this is kinetic. You'd make a Tafel plot out of it. And so to do that, first I have to swap the voltage and current axes. I know you can't see the sub menus, but I can do a mathematical operation here where I swap the X and the Y axes. Okay. And so now I have potential on the y-axis and current on the x-axis. And now all I have to do, again, I know you can't see the sub menu, I'm just doing it quickly here, is take the logarithm of the x-axis, and I get this. This is a Tafel plot. So I have voltage and I have logarithm of current, and then basically I can take a baseline, take a slope of these data here, and you can see that actually I get something that's close to, like, in this case, I think these data were maybe done, created with, like, simulated themselves. It looks actually quite perfect, almost like you can see it actually looks pretty perfectly done, or it's like maybe it was ferrocene, so it already kind of behaves perfectly. Anyway, the slope that I'm getting here is about 120 millivolts per decade, which is like perfect one electron transfer. So it's behaving quite nicely. Now, in all cases, maybe it doesn't exactly behave this way. Anyway, whether or not it behaves perfectly, this is, generally speaking, how you would approach a foot of wave analysis to make a Tafel plot and then get a Tafel slope. Okay, so there you go.
Nice. Looks like maybe we have time for the last question, and there's still a bunch of questions that we're just didn't even get around to answering.
Next week. It's always next week. We'll get to it next week. I think it's just this 3-part question here, but we can do that next week, I guess, right?
So DM is saying for ferrocyanide redox couple using 10 millimolar, ferri or ferrocyanide, solution in 1 molar potassium nitrate on the platinum RDE. I got a nice CV, but the zero current line shifted upwards. Do you know what might be the reason?
Higher drop.
Well, I want to know what he means by zero current line, because I'm thinking, like, if he did a CV and when it came back, it didn't come back to the same starting location. It came back up, shifted up. So we need, I guess, a little bit of clarification on that.
Here's my assumption and what it means based on what I would assume.
Yeah, this is
what I assume you mean. If what you mean is scenario 1, you do ferrocyanide and you get something that's like tilted or something like that. Something like, it's like this isn't flat. You know what I mean?
The zero current line.
I don't know if that's exactly.
Oh, yeah.
So
zero current line.
So perhaps implicit in your question, but you didn't list it. Oh, you did say 1 molar KNO3. Wait, okay. So,
1 molar KNO3.
Oh, 1 molar. I missed that. Okay. So this is probably not it, because I was going to say, you said 10 millimolar ferrocyanide, but I didn't see a supporting electrolyte, but I just noticed you said 1 molar. I missed that part. So, okay. So it's not a lack of, I was going to say it could be IR drop if you don't have supporting electrolyte.
Yeah.
But I don't think that's the case. So now I'm actually going to stop because I don't know what you mean. So.
Yeah, I mean, well, actually in that picture, I mean, here's a question, DM. Are you referring to the fact that if Neil completed like just that little bit of the trace on the end
on the left,
it doesn't end in the same spot, and we just drew it differently, but the current didn't end at 0, and it was, in this case it was shifted down.
You
but
could draw if you want to, I guess.
Yeah, I mean, are you talking about let's go to vanadium and zinc. But I guess this is what I thought you were referring to, is that if let's say you have your voltammogram like this. I really can't draw. God, I really cannot draw voltammograms at all, despite looking at them
all the time.
Yeah. And then no. God. But basically it's like, hey, this was 0 and now it's shifted upwards. It didn't end at the same potential. Is that what you're referring to? That's the clarifying question.
Because that's just double layer.
Well, it's a little bit more than just double layer. It can be some double layer, but I think it's also due to it's actually diffusion. So if you,
Depends how fast you're scanning, right? Yeah.
well, if you I think so. If we go to just simulation software, and if we're going, let's just do, let's see, if I simulated this voltammogram, I started here. I don't end exactly at 0. I'm shifted up by some microamps. So this, uh,
Okay, so he clarified, but I think the
yeah,
answer is still kind of what you're talking about. He says the
the
current
current.
above and below is not equal. The x-axis doesn't pass through the center.
Okay, all right. So I think it's
just diffusion, maybe.
It's yeah, so this line was at yeah, so this line was originally starts at 0. Um but
It might be a little
but
below
it might be a
0.
little bit below. It might start here, and and 0 is kind of here. So here's so I have two things. One is what is the units? Because sometimes it's like, hey, my current isn't 0. Yeah, but you have like nanoamps, right? You have like nanoamps of current. Super, super low. You're looking at noise at that particular place.
Mhm.
That's one assumption. So look at the units, because and then when you're actually doing the scanning and you go, it's like, oh, I'm getting micro, maybe even milliamps. So then it does look like it's actually starting at 0. So just clarify that. What it also means is if you're starting your experiment at some potential, you haven't identified if you're doing this at like one potential or another, but literally it just means when you started the experiment, it was at a potential where some reaction was occurring.
Yeah, there's like the current above and below is not equal. So it's like the current above is on the way back when there's still some residual reaction occurring. So
Hmm.
the current's a little higher because there's more reaction happening, or vice versa, whatever the answer is there. But like if they were the same above and below the x-axis for both directions, it would mean there's no reaction other than just double layer or something happening, and then it's perfect. It's perfectly centered or whatever. But like that might not be the case. You might still have some species, oxidizing or reducing, whichever direction you're talking about, um, on the return sweep or something like that, such that it's not going to be perfectly symmetrical. Also, you're doing it on platinum, and platinum has a lot of
Yeah, stuff.
stuff that it does. For instance, depending on the potential you're at, there's actually only a very narrow window with which platinum itself is like completely like nothing, quote unquote, is happening,
Yeah.
but double layer, and it's like a 50 millivolt window at like plus 300 millivolts versus NHE or something. Like it's
Mhm.
the little narrow band gap, not band gap, good lord, the little gap um, after the hydrogen adsorption desorption region and before the oxygen reduction region.
Well, this is
So
1
I'm just
molar KNO3. So he won't be seen as much like
you're still
stuff
going
from
to get a
acid.
platinum oxide
Yeah.
like peak, whether it's oxygen reduction or not. You still get a little bit of platinum
Yes.
oxidation wave, and you get an oxidation, the reduction of the PTO, even if it's not like ORR in solution. You
Hmm.
still get a platinum oxide reduction in oxidation, and you get platinum hydrogen at low potentials. Like my point is, some of the asymmetry might also have to do with just platinum is in a potential window where it's doing something too.
Yeah.
Like platinum is, most of the time I think with like ferro for these kinds of things, people use glassy carbon because it does have mostly a totally non-contributing background, basically.
Hmm.
Platinum is great as a catalyst. And it's kind of funny. We always use the word inert, and it's correct in some sense. Like of noble metals, it's relatively unchanged at almost any potential. It performs catalytically very, very well, but it's not inert when you consider like that it does a lot of crap in the background.
Yeah.
Such that like if you're doing like there's a reason why we use carbon, for instance, as a substrate for other catalysts, because
Hmm.
carbon really just doesn't do anything and contribute. It's a very poor like oxygen reduction catalyst. It's a poor HER, it's a poor OER catalyst. Like it's good that it's bad at those things. So when you put platinum or ruthenium or something on it,
Hmm.
all of your activity mostly can be attributed to the thing that you put on carbon, right? But if you put like some material on platinum and you want to be like, how good does this do oxygen reduction? It's like, okay, well, platinum itself does really well. So how do you get rid of that effect? It's like you're confounding it a little.
Mhm.
So anyway, I think that is possible. That's part of the, I don't know, asymmetry of the above and below the x-axis that you're observing as well.
Mhm.
But I also think that, like you said, it has a lot to do with just diffusion or
Well,
residual processes.
yeah, I mean, in the example I had, it doesn't end on the axis because there is still some molecules that are continuing to do the well, at least in that case, it was like an oxidation reaction. It was still oxidizing, even though it was a very low concentration. It was still oxidizing, and just based on simulation. So yeah, there's double layer capacitance. There's also diffusion of your species.
Hmm.
So yeah. Well, it's 3:05 right now. So and
Do you want to leave this 3-part thing for next week? It probably requires a little more time.
yeah,
So
probably requires a little bit more time. He did ask a question that was already technically answered, so we don't need to go
that is
through that.
yeah.
And in a way, we did talk a little bit about the potential window, but we can talk a little bit more about
We'll
it
leave
if
it
we
in
need
case
it.
we need to address it. But we did, the question was about OER, HER, potential window, and then let's see. Yeah, like where the onset potential, how do you, to a certain
Yeah.
extent, you already answered it with the potential window. Like you have to
Yeah.
experiment and go and find where the stuff is happening, so to speak. But
Yeah.
we'll leave it in our catalog of
Yeah.
unanswered questions that we keep trying to get to. And if we are
we ever
able
get
to
to them.
directly address it, we will. But we did talk about those concepts today. So hopefully
Yeah.
that'll kind of suffice. So,
Yeah.
all right. Yeah, we're going to leave it there, I think,
Yeah.
for the day, for the weekend, for
Mhm.
everything. It is Friday after all.
Yes.
So, all right. Well, thank you everybody again. Thank you for your questions. Thank you for watching this, whether you're watching us live or later. And I guess we will see everybody next week, and have a good one.
Yep. See you later.